If you were born on the moon, you could never come to Earth. Your bones wouldn't survive it. Your heart couldn't handle it. Gravity alone would be enough to kill you, and we haven't even gotten to the radiation. We are talking about creating a version of the human species that can never come home. Are we ready for what it takes to colonize the moon? And here is a question. If you could genetically modify one thing about the human body to make it better suited for space, what would you change? Let me know in the comments. I will pin the most creative answer. Now let's begin. The moon is not just a big rock floating nearby. It is, by every meaningful measure, a completely alien world. It formed roughly 4.5 billion years ago, about the same time the Earth did. Most scientists today support what's called the giant impact hypothesis. The idea goes like this. Very early in Earth's history, a Mars-sized object, scientists call it Theia, slammed into our young planet with unimaginable force. The collision blasted enormous amounts of debris into orbit. Over time, that debris clumped together under gravity and became the moon. In a very real sense, you and the moon are made of some of the same ancient stuff. We are all, as the late Carl Sagan beautifully put it, made of star stuff. And the moon? It is essentially Earth's oldest sibling, born from the same violent, chaotic beginning. But the 4.5 billion years since that collision have taken the moon and the Earth in radically different directions. Earth got an atmosphere. Earth got liquid water. Earth got tectonic plates that constantly resurface and renew the landscape. Earth got magnetic fields that wrap around the planet like an invisible shield. Earth got life, which then changed the atmosphere, which then changed the temperature, which then made more life possible. A beautiful, self-sustaining loop stretching across billions of years. The moon got none of that, and that's not a small detail. That is everything, because almost every single feature of Earth that makes human life possible, that allows a human body to exist at all, is the product of those 4.5 billion years of active living, dynamic planetary evolution. The moon sat still, it froze, it became a kind of time capsule, preserved almost exactly as it was when the solar system was young. So when you think about putting a human being on the lunar surface for months or years at a time, you're not just talking about dropping someone off in a hostile desert or a frigid polar region. You are talking about placing a creature, one whose every cell, every organ, every biochemical process was shaped by Earth, into an environment that Earth's biology has never once encountered in the entire history of life. That is not a small ask. That is one of the most audacious things our species has ever seriously considered. Now let's talk about what that environment actually looks like. Because once you understand it, truly understand it, the scale of the biological challenge becomes almost overwhelming. First, let's talk about temperature. And I don't mean regular hot or cold uncomfortable. I mean something that would destroy most Earth technology within hours if it wasn't specifically engineered to handle it. The moon has no atmosphere. None. That means there is nothing to trap heat, nothing to distribute warmth across the surface, and nothing to buffer the wild swings between sunlight and shadow. On Earth, our atmosphere acts like a blanket. It keeps the daytime from getting too scorching and keeps the nighttime from getting too deadly. It moderates everything. On the moon, there is no blanket. The sun beats directly down onto the surface with zero filtering, and temperatures on the sunlit side can climb to around 127 degrees Celsius. That is roughly 260 degrees Fahrenheit, hot enough to boil water in certain conditions. And then the moment you step into the shadow, or the lunar night begins, temperatures can plummet to negative 173 degrees Celsius. That is roughly negative 280 degrees Fahrenheit. One of the coldest temperatures on the surface of any body in the entire inner solar system. And here's where it gets stranger. A single lunar day, from one sunrise to the next, lasts about 29.5 Earth days. That means the moon bakes in direct sunlight for roughly 2 Earth weeks straight, and then it sits in total darkness for another 2 weeks. Not the kind of darkness where your eyes adjust and you can start to make out shapes. Complete, total, absolute darkness. No stars visible, no ambient light, no warmth, just cold and black. Now stop and think about what this means for a human colony. Your circadian rhythm, your body's internal 24-hour clock, has been tuned by millions of years of evolution to respond to sunlight and darkness cycling every single day. Sunrise tells your body to wake up, get alert, start producing cortisol. Sunset tells your body to wind down, start producing melatonin, prepare for sleep. Every major biological system in your body, your hormones, your immune function, your digestion, your heart rate, your mood, runs on the rhythm of Earth's 24-hour day. On the moon, that rhythm is completely shattered. You'd be living in a habitat where the light outside your window doesn't change for 2 weeks at a time. You'd have to create artificial cycles of day and night inside your base just to keep your biology from completely unraveling. And even then, even with artificial lighting and strict schedules, research on astronauts aboard the International Space Station tells us that maintaining healthy sleep patterns in space is extraordinarily difficult. Studies show that ISS astronauts frequently experience poor sleep quality and disrupted circadian rhythms even with countermeasures in place. On the moon, far from Earth's protective magnetic field, far from the natural cues your body has relied on since the day you were born, that challenge becomes even more severe, and that's just the temperature and light. We haven't even gotten to the radiation yet, or the gravity, or the dust, or what happens to your mind. But here's the thing I want you to hold on to as we move through all of this. The human body is remarkably adaptable. That's not just an inspirational phrase, it's literally true. Our species has managed to survive in environments ranging from the frozen tundra of Siberia to the scorching deserts of the Sahara. We've climbed to the top of Everest, where the oxygen is so thin that most animals couldn't survive for minutes. We've descended to the crushing depths of the ocean. We've even learned to live for months at a time in the microgravity of the International Space Station. Every single time the human body encounters a new environment, it begins, slowly, imperfectly, sometimes painfully, to adapt. And the question that drives the most cutting-edge research in space medicine, astrobiology, and neuroscience right now is not just whether humans can visit the moon. It's whether we can adapt deeply enough, thoroughly enough, and quickly enough to actually make a permanent home there. And the honest answer that science gives us today is, we don't fully know yet, but we're learning. And what we're learning is both humbling and absolutely breathtaking. Because to truly colonize the moon, human beings wouldn't just need better technology. They might need to become, in some very real biological sense, something slightly different from what we are today. Not in some distant science fiction future, potentially within the lifetimes of people alive right now. That's where we're headed in this video. In the next sections, we're going to walk through every major biological system in your body, your skeleton, your muscles, your cardiovascular system, your DNA, your lungs, your brain, and we're going to look at exactly what the lunar environment does to each one of them. Then we're going to ask the deeper question: what would genuine adaptation look like? What would a human being who was truly suited for the moon actually be like? And finally, we're going to zoom out, because this isn't just a conversation about the moon. This is a conversation about the future of our species, about who we are and who we might one day become, about what it means to take life, this fragile, improbable, magnificent thing, and carry it out beyond the cradle of Earth into the wider universe. You are made of atoms forged in dying stars. You carry within you the history of 4 billion years of evolution on a small blue world, orbiting an ordinary star in a galaxy of 400 billion stars, in a universe of perhaps 2 trillion galaxies. That is who you are, that is where you come from, and now, for the first time in that entire 4 billion year story, your species is seriously asking whether it can call another world home. How incredible is that? Let's talk about gravity, or more specifically, let's talk about what happens when you don't have enough of it. Right now, as you watch this video, gravity is doing something to you that you almost never think about. It is pulling on every single cell in your body, every bone, every muscle fiber, every blood vessel, every organ. All of it is under constant, gentle, relentless gravitational stress. And your body, shaped by millions of years of evolution on a one-gravity world, has learned to interpret that stress as a signal that says, stay strong, stay dense, stay ready. Your skeleton is not a passive structure. It is a living, dynamic tissue that is constantly being broken down and rebuilt. Specialized cells called osteoclasts dissolve old bone material, while other cells called osteoblasts lay down fresh new bone in its place. This cycle, called bone remodeling, happens continuously throughout your life, and one of the primary signals that tells your osteoblasts to keep building is mechanical load. The simple act of carrying your own weight through a gravitational field tells your bones you are needed. Stay strong, roam that signal, and the system begins to fall apart. We've known this for decades now, thanks largely to research on astronauts aboard the International Space Station. In the microgravity environment of low Earth orbit, astronauts lose bone mass at a rate of roughly 1 to 2% per month. That might not sound dramatic until you put it in context. The average older adult experiencing osteoporosis, one of the most debilitating bone diseases on Earth, loses bone at a rate of about 1 to 2% per year. Astronauts in space can match that rate in a single month. After 6 months aboard the ISS, some astronauts have returned to Earth with bone density losses in the hip and spine that resemble those of someone decades older, and critically, not all of it comes back. Even with intensive rehabilitation, some of that bone loss appears to be permanent. The skeleton that returns from space is not quite the same skeleton that left. Now here's something crucial. The International Space Station operates in microgravity, effectively zero gravity. The Moon is not zero gravity. Lunar gravity is about 1/6 of Earth's. So you might think, well, that's better than nothing, right? And in some ways, yes. 1/6 gravity is meaningfully better than zero, but research suggests it is nowhere near enough to maintain a healthy human skeleton over the long term. We don't yet have definitive data on what 1/6 gravity does to bones over years or decades, because no human has ever lived in 1/6 gravity for that long. But the trajectory of what we know from both spaceflight research and bedridden patients on Earth suggests the outcome would be serious. Think about what this means for a permanent colony. Children born on the Moon, growing up in 1/6 gravity, would be developing their skeletons in a fundamentally different gravitational environment than any human being in history. Bone development in childhood and adolescence is profoundly shaped by mechanical loading. A child on the Moon would likely develop bones that are longer, more slender, and significantly less dense than those of a child raised on Earth. Over multiple generations, this could produce bodies that are structurally adapted to 1/6 gravity, but which might literally be unable to survive the crushing load of full Earth gravity if they ever tried to return. This is not science fiction. This is the logical extrapolation of well-established bone physiology applied to a new gravitational environment. And some researchers believe it represents one of the most serious long-term challenges of lunar colonization, but bones are only part of the story. Let's talk about muscles. Your muscles, like your bones, are maintained by the constant work of moving against gravity. Every time you stand up from a chair, Every time you climb a flight of stairs, every time you carry a bag of groceries, you are giving your muscles a reason to stay strong. The moment that reason disappears, muscles begin to atrophy, to shrink and weaken with startling speed. In space, this process begins almost immediately. Without the constant resistance of gravity, muscle fibers begin to break down faster than they are rebuilt. Astronauts on the ISS follow rigorous exercise regimens, sometimes 2 hours of physical activity per day, specifically to slow this process. And even with all of that effort, muscle loss in space remains a significant problem, particularly in the postural muscles of the legs, back and core that do most of the work of keeping you upright on Earth. In 1/6 gravity on the Moon, the demands on those muscles would be dramatically reduced. Moving around would feel effortless compared to Earth. In the short term, that might actually feel wonderful. But over months and years, those muscles would adapt to their new reality. They would become optimized for a 1/6 gravity world, lighter, less powerful by Earth standards. And just like with bones, this raises a profound question about multi-generational colonization. What would a person look like, physically, after 5 generations of being born and raised on the Moon? We genuinely don't know, but the physics and biology suggest they would be taller, with a more slender build, with less muscle mass and lower bone density than their Earth counterparts. Not weaker in the context of their environment, they'd be perfectly suited for moving around in lunar gravity, but potentially fragile by the standards of the world their ancestors came from. They might be a new kind of human, not by choice and not by design, just by adaptation. Now let's go even deeper. Let's talk about your heart. The cardiovascular system is one of the most gravity-dependent systems in your body, and most people never think about it that way. Here on Earth, your heart works hardest to pump blood upward against gravity to supply your brain and upper body. Your blood vessels have evolved a complex system of valves, muscle tone, and pressure regulation specifically designed to fight gravity's constant downward pull on your blood. In reduced gravity, that fight becomes unnecessary. And when a biological system no longer needs to perform a certain function, it stops performing it as efficiently. This is one of the most fundamental principles in evolutionary biology: use it or lose it. In space, one of the first things that happens to the cardiovascular system is a fluid shift. Without gravity pulling blood toward the lower body, fluid redistributes upward toward the head and chest. Astronauts in space frequently describe a sensation of head congestion, like having a permanent mild cold, because of this upward fluid shift. The face puffs slightly, the legs thin out. The body senses that there is too much fluid in the upper body and begins to reduce overall blood volume by excreting water and sodium. This is the body trying to adapt. But it means that when an astronaut returns to Earth, their reduced blood volume can cause dizziness, fainting, and serious difficulty standing upright, a condition called orthostatic intolerance. After months in space, some astronauts have had to be carried off their spacecraft because their cardiovascular systems simply couldn't handle Earth's gravity anymore. Their hearts and blood vessels had adapted so thoroughly to a low-gravity environment that being back in full gravity felt like a physiological assault. Now imagine that process not over 6 months, but over years, over a lifetime, over generations. The cardiovascular system of a long-term lunar resident would likely adapt in fundamental ways. The heart might become smaller and less powerful by Earth standards. Blood pressure regulation systems would be recalibrated for a low-gravity world. The entire plumbing of the body, the arteries, veins, capillaries, and the complex hormonal systems that regulate them would slowly, over time, become optimized for the Moon. And here's where it gets philosophically interesting. At what point does adaptation become speciation? At what point Do the bodies of people who have lived on the moon for generations become so different from the bodies of people on Earth that the two groups are not just culturally or geographically separated, but biologically distinct? That is not a question with an easy answer, but it is a question that serious scientists are already beginning to ask. And by the way, if you're the kind of person who gets genuinely excited about the cosmos, science, and the great questions of human existence, make sure you subscribe to this channel and give this video a like. Every single subscriber helps me keep making content like this. There is one more system we need to talk about, and it might be the most surprising one of all: your vision. Space is doing something alarming to astronaut eyesight, and researchers are only beginning to understand why. A condition called spaceflight-associated neuroocular syndrome, scientists abbreviate it as SANS, has been documented in a significant number of astronauts who spend extended time in space. It involves a flattening of the back of the eyeball, swelling of the optic nerve, and changes in the brain tissue around the visual processing centers. The leading hypothesis is that the same upward fluid shift we talked about with the cardiovascular system, that redistribution of fluid toward the head, increases pressure inside the skull. And that increased intracranial pressure pushes against the optic nerve and reshapes the eye from the inside. The effects vary from person to person. Some astronauts experience only mild temporary vision changes. Others have returned from long-duration missions with permanent reductions in visual acuity, and the terrifying part is that the mechanism is not fully understood yet. We don't know exactly why some people are affected severely and others aren't. We don't know whether the changes would stabilize over time in a lunar environment or continue to worsen. We don't know whether children raised in reduced gravity would experience the same syndrome, or whether their developing bodies might adapt in ways that protect them. What we do know is that vision loss in a small, isolated lunar habitat, where every member of the crew is essential, where the margin for error is essentially zero, would be potentially catastrophic. And it represents one of the most urgent unsolved problems in space medicine today. NASA has dedicated significant research resources to understanding SANS. Scientists from the European Space Agency, from universities across the world, from research hospitals studying intracranial pressure disorders on Earth, they're all working on pieces of this puzzle. Because they know that if we're serious about long-duration human presence anywhere beyond low Earth orbit, this problem has to be solved. So let's take stock of where we are, in just the physical, mechanical aspects of lunar living: gravity, temperature, light cycles. We've already identified profound challenges to the skeleton, the muscles, the cardiovascular system, and even the eyes. And we haven't yet touched radiation. We haven't talked about the dust. We haven't gone anywhere near the psychological dimension. But here's what I want you to hold on to before we move into those territories. Every single one of these challenges is also, in a strange way, a window into something beautiful. Because studying what the human body does when you take it out of the environment it evolved in, watching which systems break down and which ones adapt, teaches us things about ourselves that we could never learn any other way. The ISS has been a laboratory not just for physics and materials science and plant biology. It has been a laboratory for understanding the human body at a level of depth and detail that was simply impossible before humans went to space. Every scan of an astronaut's bones, every measurement of their muscle mass, every vision test, every blood sample, all of it is building a picture of human biology that goes far beyond space medicine. It is illuminating how our bodies work right here on Earth, giving doctors new tools to treat osteoporosis, cardiovascular disease, and neurological conditions in patients who have never left the ground. This is what science does. It reaches into the unknown and it comes back with gifts. Let's talk about your mind. Because here's something that doesn't get discussed nearly enough in conversations about space exploration. The human brain is not a computer. It doesn't just process information and execute commands regardless of its environment. It is a biological organ, a living, feeling, deeply social organ that evolved over millions of years in a very specific kind of world. A world with open horizons, a world with fresh air and the smell of rain and the sound of wind through trees. A world where you could walk for miles in any direction and encounter other human beings. A world where, even in its most dangerous and unpredictable moments, something about the landscape was fundamentally familiar. The moon offers none of that familiarity. And what happens to a human mind when you strip away every single environmental cue it has ever known, when you place it in a small sealed habitat on a barren, airless, radiation-soaked rock 384,000 kilometers from everyone and everything it has ever loved, is one of the most complex and least understood questions in all of space science. But we're starting to get answers, and some of them are deeply unsettling. Let's begin with isolation. Not the casual kind of isolation you might feel on a rainy weekend when you don't leave the house. Real isolation, the kind that has been studied in Antarctic research stations, in nuclear submarines, in simulated Mars missions, and aboard the International Space Station. The kind where you are genuinely, physically cut off from the rest of your species for months at a time. Human beings are, at a neurological level, profoundly social creatures. Our brains are wired for connection. We have entire neural networks, sometimes called the social brain, dedicated to reading other people's faces, interpreting tone of voice, navigating relationships, and processing the emotional states of those around us. This machinery evolved because, for most of human history, being socially connected to a group was the difference between survival and death. Isolation wasn't just unpleasant, it was dangerous, and the brain treats prolonged isolation accordingly. Research on people in extreme isolation environments, whether that's long-duration spaceflight, Antarctic winter stations, or solitary confinement, consistently shows a predictable cascade of psychological effects. In the early weeks, people often feel fine. The novelty of the situation keeps the mind engaged. There is excitement, focus, a sense of purpose, but as weeks turn into months, things begin to shift. Mood becomes more volatile, irritability increases, small conflicts with crewmates, the kind that would be trivial in normal life, take on exaggerated emotional weight, concentration becomes harder, memory starts to feel less reliable. Some people experience what researchers call the third quarter phenomenon, a dramatic dip in psychological well-being that tends to hit roughly 3/4 of the way through a long mission, when the end is close enough to crave but still far enough away to feel agonizing. In more severe cases, prolonged isolation can trigger symptoms that look very much like clinical depression: persistent low mood, loss of motivation, disrupted sleep, withdrawal from social interaction, and a creeping sense of meaninglessness. In a lunar habitat, where every member of the crew is essential and where there is literally nowhere else to go, any one of these outcomes could have catastrophic consequences. Now, add confinement to the picture. Isolation and confinement are related but distinct. Isolation is about being separated from a larger social world. Confinement is about the physical constraint of space itself. And the combination of the two is, according to space psychologists, significantly more challenging than either one alone. A lunar habitat, at least in any near-future design we can currently imagine, would be relatively small. Engineers and mission planners have to balance habitability against the enormous cost and complexity of transporting and constructing structures on the lunar surface. The result is that early lunar settlers would likely be living in spaces roughly comparable to a large apartment, shared with several other people, with essentially no private outdoor space, no ability to simply go for a walk outside without donning a complex and physically demanding pressure suit, and no way to genuinely escape the presence of their crewmates. Research on confined environments gives us a vivid picture of what this does to people over time. Studies conducted in the Mars 500 simulation, a project in which 6 volunteers spent 520 days sealed inside a mock spacecraft in Moscow, found that the crew members progressively reduced their physical activity, experienced disrupted sleep patterns, and showed signs of psychological sedation, a kind of flattening of mood and motivation as the mission wore on. One crew member spent a significant portion of the mission barely leaving his private quarters, and critically, that simulation had one thing that a real lunar mission wouldn't. The participants knew they could leave if things got truly bad. There was an emergency exit. On the Moon, there is no emergency exit. The psychological weight of knowing that, of understanding at a deep, visceral level that you cannot leave, that the airless void outside your habitat would kill you in seconds, is something that no simulation has ever been able to fully replicate. Space psychologists call this ICE, isolated, confined, and extreme environments, and the research consistently shows that the extreme part is not just about physical danger. It's about the psychological burden of living in a place that is fundamentally, continuously, existentially hostile to human life. The awareness, never fully escapable, that the barrier between you and death is a few centimeters of engineered material. Let's talk about something even more subtle and in many ways more fascinating: what distance does to the human psyche. Light travels at just under 300,000 kilometers per second, the fastest speed in the universe. From the Moon to Earth, a radio signal traveling at the speed of light takes about 1¼ seconds to arrive. That doesn't sound like much, but in human communication it matters. A 1¼ second delay in each direction means a 2½ second round trip for any conversation. Every exchange has a pause built into it. Every attempt at real-time conversation has a strange, slightly disorienting lag. It's not enough to make communication impossible, but it is enough to make it feel different, and over months and years, that subtle wrongness, that tiny but constant reminder that you are not there, you are not home, you are somewhere else entirely, accumulates in ways that researchers are only beginning to quantify. For comparison, consider what communication delay does in even more extreme scenarios. A signal to Mars, depending on where the two planets are in their orbits, can take anywhere from 3 to 22 minutes one way. At those distances, real-time conversation becomes impossible. You speak, you wait, you might do other things for half an hour, you receive a reply. It starts to feel less like a conversation and more like exchanging letters. That fundamental shift in the texture of human connection, in the feeling of being heard, being responded to, being present with another person, is something that no one who has only ever lived on Earth has ever had to navigate. Lunar colonists would be the first human beings in history to live permanently at communication lag distance from their home civilization, and while 1¼ seconds sounds trivial, the psychological research suggests that even subtle disruptions to communication flow affect how emotionally supported people feel. They affect the sense of belonging, the sense of being connected to something larger than yourself. And belonging, it turns out, is not a luxury, it is a neurological need. There is another dimension to the psychological challenge of lunar living that is almost never discussed publicly, but which space psychologists consider one of the most serious long-term concerns: what researchers call cognitive degradation. This is not about intelligence or education. It's about what happens to higher cognitive functions: attention, decision-making, executive planning, creative problem-solving. When the brain is subjected to prolonged stress, sleep disruption, radiation exposure, and sensory monotony simultaneously, studies on Antarctic expeditioners, submarine crews, and long-duration astronauts all point in the same direction. Under ice conditions, cognitive performance declines, reaction times slow, errors in complex tasks increase. The ability to assess risk accurately, crucial for survival in a dangerous environment, becomes subtly impaired. People become overconfident in some domains and irrationally cautious in others. The social dynamics of small, confined groups begin to exert a disproportionate influence on individual decision-making, sometimes leading to poor group choices that no individual member would have made alone. This phenomenon has a name in social psychology: groupthink. And in a small lunar crew where social harmony feels existentially important, where any serious interpersonal conflict feels potentially catastrophic, the pressure to avoid disagreement, to go along with the group, to smooth over problems rather than confront them honestly, could be enormous. The irony is brutal. The environment that most demands clear-headed, accurate, independent thinking is also the environment most likely to erode exactly those capacities over time. But here is where the story takes a turn that I find genuinely awe-inspiring. Because the human mind, just like the human body, has a remarkable capacity to adapt. And some of what we're learning about how people cope with ice environments is not just sobering, it is genuinely beautiful. Research on the most psychologically resilient people in extreme environments consistently identifies a cluster of traits and strategies that seem to protect the mind against the worst effects of isolation and confinement. One of the most powerful is meaning-making, the ability to connect your daily experience, however difficult, to a larger sense of purpose. People who frame their suffering not as something happening to them, but as something they are choosing in service of something greater than themselves, show dramatically better psychological outcomes than those who don't. Antarctic researchers who think of themselves as pioneers of human knowledge, as people doing something important for humanity, fare better than those who focus primarily on the hardship. ISS astronauts who maintain a strong connection to the scientific mission of their work, who can look out the cupola window at Earth below and feel genuine wonder, show better psychological profiles than those who become task-focused and disconnected from the larger context. This is not wishful thinking. It is measurable. It shows up in hormone levels, in sleep quality, in cognitive performance metrics, in the quality of communication between crewmates. Meaning is not just a philosophical luxury. For the human brain, it appears to be a genuine physiological resource. And this is why the way we frame the story of lunar colonization matters enormously, not just for public engagement or inspiration, but for the actual survival and well-being of the people who will one day live there. They will need to understand, at the deepest possible level, why they are there, what it means, what it could lead to. They will need to feel in their bones that they are part of something worthy of the sacrifice, because the moon will ask a great deal of them, and the mind that endures, the mind that adapts, the mind that perhaps even thrives in that alien and unforgiving place, will be one anchored to something larger than itself. We are, after all, a species that has always drawn strength from story, from meaning, from the sense that our journey, however painful, is going somewhere. There is a killer on the moon, and you cannot see it, you cannot feel it, you cannot smell it or hear it or taste it. It produces no sound, no heat, no visible light. It passes through walls, it passes through suits. In some forms, it passes through nearly everything. And it is working silently and continuously to rewrite the molecular instructions inside every single cell in your body. It is radiation, and on the moon it is everywhere. To understand why, you have to understand what protects you from it, right here on Earth. Because right now, as you sit watching this video, You are being bombarded by radiation from space, cosmic rays, high-energy particles accelerated to near the speed of light by supernovae, black holes, and other violent cosmic events are streaming through the universe in every direction. Solar energetic particles, bursts of charged particles thrown out by the sun during solar flares and coronal mass ejections, periodically sweep through the inner solar system like invisible storms. All of this is real. All of it is happening right now, and almost none of it reaches you. You are protected by two overlapping shields that you have never had to think about, because they have always just been there. The first is Earth's magnetic field, a vast, invisible bubble of magnetism generated by the churning of liquid iron in our planet's outer core. This magnetosphere deflects and traps charged particles, channeling them toward the poles where they create the aurora borealis and the aurora australis instead of raining down on populated areas. Without it, the surface of the Earth would be a very different and far more dangerous place. The second shield is the atmosphere itself. Even for radiation that makes it through the magnetosphere, Earth's atmosphere, roughly equivalent in protective mass to about 10 meters of water above your head, absorbs and scatters a significant portion of it before it reaches the ground. High-energy particles collide with air molecules and break apart into secondary particles, which in turn break apart again in a cascade that dissipates much of the energy before it arrives at the surface. The Moon has neither of these protections. The lunar magnetic field is a ghost of something that died billions of years ago. What remains is a patchy, weak remnant, not a global shield, just scattered magnetized regions in the crust, locally significant but globally irrelevant, and the lunar atmosphere, as we discussed in Part 1, is essentially non-existent, a wisp of gas so thin it barely registers. There is no column of air above a lunar colonist's head to break apart incoming radiation. There is nothing between them and the full, unfiltered fury of the cosmos. Let's talk about what that actually means for the human body. Radiation damages biological tissue primarily by ionizing atoms, stripping electrons from molecules and leaving behind chemically reactive fragments called free radicals. These free radicals then attack nearby molecules including proteins, cell membranes, and most critically, DNA. Most of the time, your body's sophisticated DNA repair machinery catches the damage and fixes it before it causes any lasting harm. But radiation exposure, particularly the high-energy heavy ions found in galactic cosmic rays, can cause damage so severe and so complex that the repair machinery makes mistakes. It misreads the damage, it patches things together incorrectly, and those incorrect patches, mutations, can accumulate over time. Some mutations are harmless, some are corrected by other cellular processes, but some trigger cancer, and some, in particularly sensitive cells, can cause other problems entirely. NASA has established radiation exposure limits for astronauts, measured in units called millisieverts. The average person on Earth receives about 2.4 millisieverts of radiation per year from all natural sources combined. An astronaut aboard the International Space Station, which is still protected to some extent by Earth's magnetic field, receives roughly 200 millisieverts per year. That is already a significant increase. On the lunar surface, the numbers get considerably worse. Estimates based on data from NASA's Lunar Reconnaissance Orbiter and from measurements taken during the Apollo missions suggest that a lunar colonist would receive somewhere in the range of 380 to 450 millisieverts per year during normal conditions. That is approaching 200 times the annual dose of the average person on Earth. But normal conditions on the Moon are not the only conditions to worry about. Solar energetic particle events, the bursts of high-energy particles thrown out by the Sun during major flares and coronal mass ejections, represent a different, and in some ways more acute danger. These events can deliver extremely high radiation doses in a matter of hours. During a major solar energetic particle event, an unprotected astronaut on the lunar surface could receive a dose that causes acute radiation syndrome, the condition more commonly known as radiation sickness, within a single day. Acute radiation syndrome is not subtle. At moderate doses, it causes nausea, vomiting, fatigue, and a dramatic drop in white blood cell counts that leaves the immune system severely compromised. At high doses, it causes damage to the gastrointestinal tract, the nervous system, and can be fatal within weeks. The dose required to cause acute radiation syndrome in an unprotected individual on the lunar surface during a major solar energetic particle event is, depending on the severity of the event, entirely plausible. The Apollo astronauts were lucky in this respect. None of the Apollo missions coincided with a major solar energetic particle event. Had they done so, the consequences for the crew on the lunar surface could have been catastrophic. Researchers have calculated that if the large solar flare event of August 1972, which occurred between the Apollo 16 and Apollo 17 missions, had happened while astronauts were on their way to the moon or on the surface, the crew could have received a life-threatening radiation dose. That was a near miss that most people have never heard about. For a permanent lunar colony, the question is not whether a major solar energetic particle event will occur during the colony's lifetime. It absolutely will. The question is whether the colonists will have adequate warning and adequate shelter to survive it. Warden systems are improving. The network of solar observation spacecraft, including NASA's Solar Dynamics Observatory, the Solar and Heliospheric Observatory, operated jointly by NASA and the European Space Agency, and more recent missions, provides increasingly sophisticated monitoring of solar activity. Scientists can now detect the early signs of a major solar event and issue warnings with lead times measured in hours. On Earth, this gives power grid operators and satellite managers time to take protective action. On the Moon, it would give colonists time to get underground. That word is going to come up again and again in any serious discussion of lunar colonization, because the most effective protection against both solar energetic particles and the chronic bombardment of galactic cosmic rays is mass. Lots of it: rock, regolith, water, anything with sufficient density to absorb and scatter incoming particles before they reach human tissue. The lunar surface itself, paradoxically, offers some of the best radiation shielding available on the Moon because the Moon is covered in it. Lunar lava tubes, enormous underground tunnels carved out billions of years ago by flowing lava, have been identified by orbital reconnaissance as potential natural shelters. Some of these tubes are estimated to be hundreds of meters wide and potentially kilometers long. The rock ceiling above them would provide shielding equivalent to several meters of water, which is enough to reduce radiation exposure to levels much closer to what we experience here on Earth. Building a colony inside a lunar lava tube rather than on the open surface is one of the most widely discussed strategies in serious lunar architecture. The Japan Aerospace Exploration Agency, JAXA, has published research identifying specific lava tube systems near the lunar equator that could be candidates for habitation. NASA and several private space companies have also explored the concept. The engineering challenges are immense. You would essentially be constructing a pressurized city inside a cave, but the radiation protection benefits are substantial enough that many researchers consider it the only viable long-term solution. Now, let's talk about something that is only beginning to receive serious scientific attention: what chronic radiation exposure does specifically to the brain. For decades, the primary focus of space radiation research was cancer risk, and that remains a serious concern. NASA's models suggest that astronauts on long-duration deep space missions face a meaningfully elevated lifetime risk of cancer compared to the general population. But more recent research has revealed something potentially even more alarming. Radiation may be doing things to the brain that have nothing to do with cancer at all. Studies conducted at NASA's Space Radiation Laboratory at Brookhaven National Laboratory have exposed mice to simulated space radiation, specifically the high-energy ions found in galactic cosmic rays, and then studied the effects on brain function. The results have been striking. Irradiated mice show significant impairment in cognitive tasks involving memory, spatial navigation, and decision-making. They exhibit increased anxiety-like behaviors. They show signs of neuroinflammation, an abnormal immune response within the brain tissue that persists long after the radiation exposure has ended. At the cellular level, researchers have found that high-energy heavy ions can damage the complex branching structures of neurons, the dendrites and synapses that form the physical basis of memory and cognition, in ways that are different from and potentially more damaging than other forms of radiation. These particles are so energetic that they can travel in a straight line through multiple cells simultaneously, leaving a trail of damage that the brain's repair mechanisms struggle to address. Charles Limoli, a professor of radiation oncology at the University of California, Irvine, has been one of the leading researchers in this field. His team's work has consistently demonstrated that space-level radiation exposures produce measurable cognitive deficits in animal models, deficits that translate in principle to the kinds of impairments that would matter enormously in the context of a lunar colony: slower decision-making, impaired risk assessment, memory lapses. In an environment where a single wrong decision about a pressure seal or a life support system can kill everyone, these are not acceptable outcomes. We do not yet have direct human data on chronic cognitive effects of space radiation at lunar surface levels because no human has lived on the moon long enough to generate that data. But the animal research is alarming enough that space medicine researchers consider it one of the top priorities for resolution before any serious long-duration human lunar presence begins. There is one more dimension of the radiation problem that I want to leave you with, because it connects the physical danger of radiation to something much larger, to the question of what kind of species we are and what we are willing to risk in the pursuit of the unknown. Every single person who ventures to the moon, even for a short visit, let alone a lifetime, is accepting an elevated risk. They are accepting that their DNA will accumulate damage it would not have accumulated on Earth. They are accepting that their lifetime risk of certain cancers will increase. They are accepting that we do not yet fully understand what happens to a human brain under years of chronic cosmic ray bombardment. They are walking into uncertainty with their eyes open, and people are willing to do this. They are lining up to do this. Astronauts, researchers, and a growing number of private citizens who have signed up for commercial lunar ventures all understand, at some level, what they are accepting, and they accept it anyway because they believe that what is on the other side of that risk is worth it. There is something deeply, essentially human about that willingness. We have always been a species that walks toward the dangerous horizon. We crossed oceans in wooden boats when we had no idea what was on the other side. We climbed mountains that had never been climbed, not because it was safe, but because they were there. We sent the first astronauts to the moon on a rocket that had never been fully tested in the conditions it would face, trusting in engineering and mathematics and human ingenuity and a certain irreducible amount of hope. And yes, people died. In every era of exploration, people died. The cost of the unknown has always been paid in human lives. That is not something to celebrate, but it is something to understand. Because the alternative, never reaching, never risking, never pushing beyond what is comfortable and known, is also a kind of dying, a slower kind, a quieter kind. The radiation on the moon is real. It is dangerous. It is a problem that must be solved before we can safely make the moon a permanent home for human beings. But it is a problem that human ingenuity is already working on, in laboratories, in space agencies, in the minds of researchers who lie awake at night thinking about cosmic ray shielding and DNA repair mechanisms and the cognitive resilience of the human brain. We are, in the most literal sense possible, made of stardust. The heavy atoms in our bones, the calcium, the iron, the phosphorus, were forged in the cores of stars that lived and died before our sun was born. Cosmic rays are the fingerprints of those same stellar processes. In a strange and beautiful way, when cosmic radiation touches a human body on the surface of the moon, it is the universe reaching out to touch something made of itself. That doesn't make it safe. But it does make it profound. Buzz Aldrin called it a nuisance. Neil Armstrong called it a serious problem. And after just a few hours on the lunar surface, both men had already experienced something that neither their training nor their engineering teams had fully prepared them for. Something that clung to their suits, scratched their visors, worked its way into every seaman's seal, and smelled, when they brought it back inside the lunar module, like spent gunpowder, lunar dust. It sounds almost mundane, dust. Every home has it. Every surface accumulates it. You vacuum it up and it's gone. What could be so terrifying about dust? Everything, as it turns out, almost everything. To understand why lunar dust is one of the most serious long-term threats to any permanent human presence on the moon, you first have to understand what it actually is, because it is not like any dust you have ever encountered on Earth. It is not the soft, rounded, relatively harmless particles that settle on your bookshelves or float through a shaft of sunlight in your living room. It is something fundamentally, structurally different, and that difference has consequences that reach from the surface of a spacesuit all the way into the deep tissue of a human lung. Lunar regolith, the layer of fragmented rock and mineral particles that covers the moon's surface, has been accumulating and evolving for roughly 4.5 billion years. But unlike the regolith of Earth, which is constantly being weathered by wind, water, and biological processes, lunar regolith has been shaped by an entirely different set of forces. With no atmosphere, no water, and no life, the primary agents of change on the lunar surface are micrometeorite impacts and solar radiation. Micrometeorites, tiny particles of rock and metal traveling at extraordinary speeds, have been raining down on the moon continuously for billions of years. Each impact, no matter how small, vaporizes a tiny amount of material and shatters surrounding particles into ever finer fragments. Over geological time, this process, called impact gardening, has pulverized the upper layers of the lunar surface into an extraordinarily fine powder. The finest particles of lunar regolith are measured in microns, millionths of a meter. They are, in many places, as fine as cigarette smoke particles. But the size of lunar dust particles is only the beginning of the problem. It's the shape that makes them truly dangerous. On Earth, when rock is broken down by natural processes, the resulting particles are tumbled and smoothed. Water rolls them against each other. Wind carries them and grinds their edges. Over thousands of years, the jagged edges of freshly broken rock are worn away, leaving rounded, relatively smooth particles. Sand on a beach, dust in a field, particles that, while not harmless, are far less damaging than freshly shattered rock. Lunar dust particles have never been tumbled. They have never been smoothed. Every single particle is freshly fractured, sharp, angular, jagged at a microscopic level that makes them look, under an electron microscope, almost like shards of broken glass. Some researchers describe them as resembling tiny pieces of coral, complex, branching, irregular structures with enormous surface area, relative to their size, covered in microscopic hooks and barbs that grab onto anything they contact and refuse to let go. This is why lunar dust sticks to everything. It is not just static electricity, though that plays a role too. The lunar surface is continuously bombarded by solar wind and ultraviolet radiation, which charges dust particles electrostatically, causing them to adhere to surfaces and even, in some regions, to levitate slightly above the surface in a thin, shimmering layer. It is the physical structure of the particles themselves, their angular, clingy geometry, that makes them such a persistent and penetrating problem. The Apollo astronauts encountered this within minutes of stepping onto the lunar surface. Dust coated their suits almost immediately. It was nearly impossible to brush off. The jagged particles embedded themselves in the fabric of the suits rather than simply resting on the surface. It scratched and abraded the reflective outer layers that were critical for thermal regulation. It worked its way into the joints of the suits, increasing resistance and making movement harder. It coated the optical instruments, the camera lenses, the reflective panels on the lunar rover. After the first moonwalk, when the Apollo 17 crew, Eugene Cernan and Harrison Schmitt, returned to the lunar module and removed their helmets inside the pressurized cabin, they immediately smelled something distinctive. That gunpowder smell, and Harrison Schmitt, the only geologist to walk on the moon, almost immediately developed symptoms: sneezing, a runny nose, irritated eyes and throat. Symptoms that he later described as resembling hay fever, symptoms that persisted for hours after he had left the dust behind. Schmitt was experiencing what might be called the first documented case of lunar dust toxicity in a human being. But because the Apollo missions lasted only a few days on the surface, never long enough for chronic exposure to develop, the full medical implications were never tested. The astronauts came home before the dust could do its worst. For a permanent lunar colony, there is no coming home after 3 days. Here is what we know about what finely particulate, jagged, crystalline dust does to human lungs, based on decades of research on analogous materials here on Earth. The most instructive comparison is silica dust. The fine particles generated by mining, quarrying, and construction work involving quartz-containing rock. Silica dust particles are similarly small and similarly sharp to lunar regolith particles, and the disease caused by chronic silica dust inhalation, silicosis, is one of the oldest and most devastating occupational diseases in human history. It has been killing miners and stonecutters for thousands of years. When silica dust particles are inhaled and travel deep into the lung, into the tiny air sacs called alveoli, where gas exchange takes place, the immune system recognizes them as foreign and dispatches specialized cells called macrophages to engulf them. But the sharp crystalline structure of silica particles damages and kills the macrophages that try to destroy them. The dead macrophages release inflammatory signals. More macrophages arrive, more are killed. The result is a cycle of chronic inflammation that over years causes progressive scarring of lung tissue, a process called fibrosis. The lungs become stiffer and less efficient, breathing becomes harder. The condition is progressive and irreversible. In severe cases it is fatal. Lunar regolith is not identical to silica. Its precise mineralogical composition varies by location on the Moon, and researchers are still working to understand exactly how it interacts with lung tissue. But its physical characteristics, its fineness, its angularity, its crystalline structure, suggest that it could cause damage at least comparable to silica, and potentially worse, because lunar dust particles are in some ways even more reactive than their terrestrial counterparts. On Earth, freshly fractured rock surfaces are chemically reactive. They have broken molecular bonds that are eager to react with anything they contact, but exposure to air, water, and sunlight quickly passivates these surfaces, dulling their reactivity. Lunar dust has been in a vacuum for billions of years. Its surfaces have never been passivated. When it contacts water, as it would immediately upon entering a pressurized, humid habitat, those reactive surfaces come alive. Some researchers have raised concerns that freshly exposed lunar dust, contacting the moist tissue of the respiratory tract, could trigger chemical reactions that cause damage beyond simple mechanical abrasion. This is an area of active research. NASA's Lunar Dust Toxicology Assessment Group has been working on this question for years. Studies using lunar soil simulants, materials engineered to mimic the physical and chemical properties of real lunar regolith, have been conducted on cell cultures and animal models. The results are concerning enough that virtually every serious lunar habitat design now includes multiple airlocks, dust mitigation systems, and filtration technologies specifically designed to minimize the amount of dust that enters inhabited areas. But here is the brutal engineering reality. Keeping lunar dust out of a habitat is extraordinarily difficult. The particles are so small and so clingy that they defeat conventional sealing methods. The Apollo astronauts tried their best to brush dust off their suits before re-entering the lunar module. They were never fully successful. The dust always found a way in. For a permanent colony, where crew members would be conducting extravehicular activities, spacewalks and surface excursions on a regular basis, possibly daily, the problem compounds over time. Each excursion brings more dust into the airlock, filtration systems become clogged, suits degrade faster than expected. Seals and bearings in mechanical systems wear out at accelerated rates because dust is, at a microscopic level, an extraordinarily effective abrasive. The Apollo program's experience with dust as a mechanical problem was already significant after just a few days. The lunar rover's fenders were designed to deflect dust thrown up by the wheels. When one of the fenders on the Apollo 17 rover broke, the resulting dust spray coated everything: the crew, the equipment, the instruments, in a thick grey layer that caused immediate problems and could have ended the mission early if the crew hadn't improvised a repair using geological maps and clamps. Now imagine that fender breaking not after 3 days, but after 3 years. Imagine the cumulative effect of daily dust exposure on every mechanical system in a lunar habitat, on the solar panels that provide power, on the thermal radiators that prevent the habitat from overheating, on the external sensors and cameras that monitor the surrounding environment. Lunar dust is not just a health hazard, it is an engineering adversary of the first order, patient, pervasive, and relentless. Some of the most creative solutions being proposed for the dust problem involve changing the surface itself rather than fighting the dust directly. Researchers have explored the idea of sintering the lunar regolith using concentrated solar energy or microwave radiation to partially melt and fuse the surface particles around a habitat into a harder, more stable crust that generates less airborne dust. Early experiments with lunar soil simulants have shown that this approach can produce a surprisingly solid brick-like material. It could, in principle, be used to pave pathways around a habitat, reducing the amount of loose surface material that gets kicked up by foot traffic and equipment. Others have proposed electrostatic dust shields, systems that generate an electric field above a surface, repelling the electrostatically charged dust particles and keeping them away from critical equipment. NASA has been developing this technology for years, and prototype systems have shown promising results in laboratory conditions. Whether they will perform as well in the actual lunar environment, with its complex and variable electrostatic conditions, remains to be demonstrated. And then there are the suits themselves. Next-generation lunar spacesuit designs are attempting to incorporate dust-resistant materials and improved sealing systems that will reduce contamination during airlock cycling. Several companies working on lunar suit technology have made dust mitigation one of their primary engineering priorities. All of this is genuinely impressive. Human ingenuity, applied to a seemingly intractable problem, is finding creative pathways forward. But every researcher who works on this problem will tell you the same thing. We have not solved it yet. We have promising approaches. We have clever ideas. We have laboratory results that give reason for cautious optimism. But until those solutions are tested on the actual lunar surface, in actual lunar conditions, over actual years of operation, we won't truly know whether we've cracked it. And this brings me to something I think is worth sitting with for a moment. Because the dust problem, unglamorous, irritating, almost mundane in its physicality, illustrates something profound about the nature of the challenge we are discussing. When people imagine the obstacles to colonizing the moon, they tend to think about the dramatic ones: the vacuum, the radiation, the psychological isolation, the gravitational effects on the body. These are big cinematic challenges. They are the kind of thing that makes it into documentary films and science fiction novels. But it might be dust, humble, grey, electrically charged, microscopically jagged lunar dust. That proves to be the most persistent and difficult adversary of all. It is the kind of problem that you don't fully appreciate until you are standing on the surface, watching it coat your visor within seconds of stepping outside, feeling it grit between the joints of your gloves, smelling it when you come back inside. The universe does not always announce its most serious obstacles with drama. Sometimes they arrive quietly, sometimes they look like dust, and somehow that makes the whole enterprise feel more real, more human, because we are not just battling the cosmos in the abstract. We are dealing with the specific, particular, stubborn details of a real place. A place that will not make room for us easily. A place that will test us in ways we have not yet imagined. But we are a species that has always found a way through the details, the unglamorous, grinding, problem-solving work of engineers and scientists and materials specialists. People who spend their careers thinking about dust filtration and suit seals and electrostatic shielding is just as much a part of the human story as the astronauts standing on the surface looking back at Earth. Every great journey is made of 10,000 small solutions to 10,000 stubborn problems. The moon is waiting for all of them. If you're still watching, make sure to subscribe and give this video a thumbs up. Every video we chase the hardest questions in the universe and come back with something genuinely worth knowing. Imagine a child who has never felt rain, not just a child who hasn't seen rain recently, or who grew up in a dry climate and only experienced it a handful of times, a child for whom rain is not a memory, not a sensation, not even a fully formed concept, just something that exists in videos and stories from a world they have never touched. A child who has never felt grass under their feet, never smelled soil after a storm, never watched a horizon dissolve into distance. A child who has looked up at the sky every day of their life and seen not blue, not clouds, not the diffuse warmth of scattered sunlight, but black. A permanent, star-filled black with a brilliant blue marble hanging in it like a jewel in a dark room. That child is a lunar native, and they may be coming sooner than you think. The moment any lunar settlement becomes permanent, the moment people stop rotating in and out and start building lives that are meant to last, the question of reproduction becomes unavoidable. And with reproduction comes the single most ethically complex, scientifically uncertain, and philosophically staggering question in the entire domain of lunar colonization. What does it mean to raise a human being on the moon? Let's start with the biology, because the biology alone is enough to stop you in your tracks. We covered in earlier parts how low gravity affects the adult skeleton and muscle system, but the adult body is a finished product, shaped by a childhood and adolescence spent in one gravity. it arrives on the moon already formed. What we haven't talked about is what happens when the body is never formed in Earth gravity at all. When the very process of growth and development, the laying down of bone, the building of muscle, the maturation of the cardiovascular and neurological systems, happens from the very beginning in 1/6 of Earth's gravitational pull, the short answer is, we don't know. We have never observed it. No mammal has ever been born and raised to adulthood in a significantly reduced gravity environment. The research simply doesn't exist yet because we have never been in a position to conduct it. But what we can do is look at what we know about how gravity shapes development in Earth-based biology and extrapolate carefully. Bone development in childhood is exquisitely sensitive to mechanical loading, the process by which a child's skeleton grows from the soft, cartilaginous framework of infancy into the dense, mineralized structure of adulthood is driven in part by the stresses placed on it by movement in a gravitational field. The mechanical signals of bearing weight, of jumping and running and falling, tell the developing skeleton how strong it needs to be. Reduce those signals dramatically, as would happen in 1/6 gravity, and the developmental program would respond accordingly. A child raised on the moon would almost certainly develop a skeleton that is less dense, more elongated, and more adapted to low-gravity movement than any human skeleton in history. Their bones would not be weak in the context of their environment, they would be precisely calibrated for it. But place them in Earth gravity, and they might not be able to stand up. Literally, the bone density required to support a human body in full Earth gravity might simply never develop in a child who never experiences full Earth gravity, and it goes beyond bones. Muscle development, cardiovascular development, the proprioceptive systems that tell your brain where your body is in space. All of these are shaped by gravitational environment during the critical windows of childhood growth. A lunar-born child would develop all of these systems in a context so different from anything in human evolutionary history that predicting the outcome is genuinely beyond our current scientific capability. There is also the question of the inner ear, the vestibular system, the biological gyroscope that gives you your sense of balance and spatial orientation is calibrated during development partly by the experience of moving through a gravitational field. In a reduced gravity environment, this calibration would be different. Lunar-born children might have a sense of balance and spatial awareness that is exquisitely tuned to 1/6 gravity but profoundly disoriented by the full gravity of Earth. They might move through their environment with a fluid grace that Earth-born visitors would find almost alien and then struggle enormously if they ever attempted to make the journey home. Now let's talk about the brain, because the developing brain is perhaps the most environmentally sensitive organ in the human body, and the environment of a lunar childhood is unlike anything the human brain has ever developed in before. The sensory environment of a lunar habitat would be radically constrained compared to Earth. Children learn about the world through an enormous variety of sensory experiences, the textures of natural materials, the sounds of wind and water and animals, the visual complexity of natural landscapes, the proprioceptive richness of playing outdoors in varied terrain. Developmental psychology has demonstrated repeatedly that sensory richness in early childhood is not a luxury. It is a driver of cognitive and neurological development. The brain literally builds itself in response to sensory input, and a brain that receives a narrower range of sensory input during critical developmental windows may develop differently than one that receives the full richness of an Earth childhood. This does not mean lunar children would be less intelligent. Intelligence is not simply a function of sensory richness in childhood, but it does mean they might think differently, perceive the world differently, have different intuitions, different cognitive strengths, different emotional responses. Their brains would be shaped by their environment just as all human brains are shaped by their environments, but their environment would be unlike any that has shaped a human brain before. Consider something as seemingly simple as the concept of outside. For every human being in history, outside has meant open space, air, sky, distance, freedom of movement. It has been a fundamental backdrop of human experience, woven into language, into art, into psychology, into the deepest architecture of what it feels like to be human. For a lunar child, outside means instant death without protection. It means a suit, an airlock, a carefully managed excursion into a lethal environment. The word outside carries an entirely different emotional weight, and that difference, small as it might seem, ripples through everything. Through how the child relates to space and boundary, through their sense of safety and danger, through their relationship with the natural world, with risk, with freedom. These are not just philosophical musings. They are the kinds of deep cognitive and emotional structures that psychologists and anthropologists study when they examine how culture and environment shape the developing mind. And a lunar childhood would represent the most radical environmental departure from the human norm in the history of our species. There is a word that scientists use when they talk about populations that become reproductively or developmentally isolated from their parent group: divergence. It is the first step on the road to what, given enough time and enough generations, can become speciation, the emergence of a genuinely new biological lineage. We are not talking about speciation happening quickly. Evolution on a biological level takes tens of thousands of years at minimum under strong selective pressures. But what we might be talking about, what some researchers are already discussing openly, is something that could be called cultural and developmental divergence happening within just a few generations. People whose bodies are shaped differently, whose brains process the world differently, whose relationship to Earth, the planet their ancestors came from, is increasingly abstract, increasingly historical, increasingly like the relationship any of us have with a distant ancestral homeland we have never actually visited. At some point, and no one can say exactly when, the people of the moon might stop thinking of themselves as Earth people who happen to live on the moon. They might start thinking of themselves as something else, something new, not better or worse than Earth people, just different, adapted, native. And when that happens, when a community of human beings on another world begins to develop its own identity, its own culture, its own sense of who they are and where they belong, something profound and irreversible will have occurred. Something that has not happened since the first humans crossed the land bridge into the Americas, or set foot on islands that no human foot had ever touched before. A new branch of humanity will have taken root in the cosmos. The psychological dimension of growing up on the moon is equally rich and equally uncharted. What does it do to a child's developing sense of self to know, from the earliest age, that they are among the first of their kind, that they are a pioneer not by choice but by birth, that the world they know, the only world they have ever known, is one that most human beings will never experience. There is research from children raised in extreme or unusual environments, the children of Antarctic researchers, of submarine families, of communities in remote and isolated corners of the world, that gives us some clues. These children often develop an unusually strong sense of identity and community within their small group. They tend to be resourceful, adaptable, and comfortable with uncertainty in ways that children raised in more conventional environments sometimes are not. They also sometimes struggle with a sense of displacement when they encounter the larger world, a feeling of being simultaneously special and isolated that can be difficult to navigate. For lunar children, these dynamics would be amplified to a degree that has no real precedent. Their community would be tiny, their isolation would be total. Their sense of being different from the rest of humanity would be not just cultural but potentially biological, and the blue marble hanging in their sky, beautiful, distant, impossibly alive with color in a black and airless universe, would be both their heritage and their horizon, something they came from but perhaps can never fully return to. What stories would they tell about Earth? What myths would grow up around it? What would it mean, in a community of lunar natives several generations deep, to speak of home, knowing that home is a place your great-grandparents left, a place your body may no longer be able to survive, a place you can see every day but may never touch? These are not engineering problems, they are the deepest kind of human problems. The kind that have always accompanied the movement of our species into new and unknown territory. The kind that get worked out not in laboratories but in kitchens and schools, and around whatever passes for a campfire in a pressurized lunar habitat. They are the problems of becoming. And here is what I want you to hold on to as we move into the final stretch of this story. Every single challenge we have discussed, the broken bones, the damaged hearts, the radiation, the dust, the isolation, the cognitive strain, the profound uncertainty of raising children in an alien world. Every single one of these challenges is also a testament to something extraordinary. The fact that we are asking these questions at all means that we are serious. It means that the dream of becoming a multi-world species has moved in our lifetimes from science fiction to science, from fantasy to planning, from impossible to merely very, very hard. And very, very hard has never stopped us before. The first lunar children, whenever they arrive, whatever they look like, however, their bodies and minds have been shaped by their extraordinary environment, will inherit a legacy that stretches back not just to the Apollo astronauts, but to the first human beings who looked up at the moon and felt something stir inside them: curiosity, wonder, the ancient, inarticulate sense that there is more out there and that we are meant to find it. Those children will be us, transformed, adapted, reaching further than any human being has ever reached before. And they will look back at Earth the way we look up at the stars. We have walked through the bones that weaken, the hearts that shrink, the muscles that forget what it means to carry weight. We have sat inside the minds of people sealed away from the rest of their species, watching Earth turn slowly in a black sky. We have talked about radiation that rewrites DNA one particle at a time, and dust so sharp and so ancient it can scar a lung from the inside. We have imagined children who will never feel rain, who will never stand on grass, who will look at the blue marble in their sky and call it something between a homeland and a legend. And now I want to ask you something. Does any of that make you want to stop? Because I don't think it does. I don't think it does for most people when they really sit with it. Because the terrifying problem with colonizing the moon is not actually the radiation or the gravity or the dust. The terrifying problem is that we are going to do it anyway. We are going to send people there, people who know the risks, who have read the studies, who understand in precise scientific detail what the moon will ask of their bodies and their minds, and those people are going to go, willingly, eagerly, because that is what we do. We have always done this. We have always walked toward the difficult horizon, not because it was safe, but because something in us, something ancient and stubborn and quietly magnificent, has never been satisfied with staying where we are. The moon will change us. There is no version of this story where it doesn't. Our bodies will adapt. Our minds will adapt. Our children will be born into a world so different from the one that shaped every human being in history that they may, in the most literal biological sense, become something new. Not a different species, not yet, but a different expression of what it means to be human, shaped by low gravity and starlight and the particular, profound loneliness of living 384,000 kilometers from the rest of your kind. And maybe that is not a terrifying problem after all. Maybe it is the oldest human story, told in a new and extraordinary place. The story of a small group of people at the edge of everything they know, building something from nothing in a hostile and indifferent world. And somehow, against all reason, making it home. We are made of stardust. Every atom of calcium in our bones, every iron atom in our blood, was forged in the heart of a dying star billions of years before our sun was born. We have always been creatures of the cosmos. We have just spent the last few 100,000 years forgetting it. The moon is how we begin to remember. If this video made you think, made you feel, made you look up at the night sky just a little differently, then share it with someone who needs to see it. Leave a comment below telling me what part hit you hardest. And subscribe if you want to keep going deeper into the universe together, because we are just getting started